Hi, I am Justin G0KSC and thanks very much for coming back to my channel. Hopefully this is going to be some more information that's going to be useful to you, and we're going to be discussing one area of balance today. But just before we move on, I just want to thank the sponsor Moonraker Online for all your radio requirements, not just in the UK but Europe-wide and worldwide also. They're making it possible for us to make these videos for you today. So the subject today is baluns, and in particular baluns within Yagi antennas. And what I want to do is to cover why they are so important and why perhaps we miss the importance of them with other antennas such as verticals or dipoles. So specifically I'm going to be covering the Yagi side. This would also be the same for quads as well, and if you haven't got the right arrangement in place as far as a balun, what the impacts are, which can be quite catastrophic, and I'll demonstrate those to you now. So I'm not going to be looking at you very much because I've got the camera, which is a new camera, just to one side, and we're going to be covering, or I'm going to be looking at the screen and explaining to you what's going on here. So I'm going to zoom this in for you so that you can see. This is a visual representation from EasyNet, the modeling software, and it shows a dipole with the feed point in the center, and then the vertical section, which is labeled number 4, is representative of a piece of coax. Now the dipole here, you have the segmentation dots, which are the measurement points that the software uses for measuring current distribution, and the same down the coax as well. Now this isn't a perfectly balanced dipole, so the coax here, there's no coax radiation, there's no current going back down the coax. So the pink line here, which is this nice curve, represents a nice even current distribution through the driven element itself. So you can see it drops off to the ends where it's just going to be voltage based, and in the center it's much higher current and low voltage, and then drops off again towards the end. So that's the first one. Now what's the consequences if we don't have a balun in place? That'll be the next picture here. So if we look at this one, in this case, and we zoom in again here, now we have current distribution along the coax itself. You can see from this pink line that there's now current radiation on the coax, and you'll see that what that's done is you have current in the hot side, or where the center side of the coax is connected to the driven element, but on the cold side there's virtually no radiation at all. And it's as I said in the last video, when you look at coax cable where it splits, the point where the coax actually splits and is no longer coaxial any longer is where your dipole starts. It doesn't, RF doesn't wait until it gets to the terminal connections, and that's why we have to eliminate that Y shape as much as possible and make a T shape at the feed point with the coax connections here. Now with the inner core of the coax, of course, it's a nice hard and fast rule where the drive or the driven element starts and coax starts, because it's either exposed or it's enshrouded by the braid. So there's no issue there. RF's only going to radiate on the driven element, which is what this side is. However, with coax, it's the inner core is taken out, so that's on this side, but then the braid is connected to this side, but there's no definitive point to say to the RF, right, stop radiating. So of course it can just travel back down the coax, and then you get a much bigger element, if you like, on that side. Now why that's perhaps not seen so much by so many people as being an important thing is that twofold really. Firstly, when you have a dipole like this and you don't have a balun in place, you're probably still going to have a good SWR. In fact, you might even have a better SWR than if you had a choke or current balun in place, a one-to-one balun in place. The reason for that, of course, is that rather than any reflected power going back down the coax and pushing on your PA, it's being radiated along the coax on the way back. So of course there's less getting back to the transceiver and the PA to present that return. So and the second point is that if you've got this horizontal dipole that's configured in this way, you've still got radiating elements. Okay, it's not all horizontally polarized. you've got some vertical aspect to it as well. And it might be the other way around. If you've got a center fed dipole that's vertical and you've got the coax coming off without a balun in place, that you've got some horizontal radiation there. And apart from, you know, interference that it could cause and high levels of RF in the shack and things like that, it's not going to be detrimental or too detrimental. However, let's now consider the scenario where this dipole and this dipole are a part of a Yagi, where that illumination of the dipole needs to be in the dipole in order to excite the parasitic elements either side of it. If some of that is lost in the coax, then of course the performance of the Yagi and how much gain it's going to have, how much power is going to be radiated in the direction that you want it, could be substantially reduced. So let's have a look here. We had discussed the Optes Yagi a few weeks ago, and I've brought this one back here again now. So if we look at this, I now have this Yagi with the reflector, the driven element here, D1, D2, D3, D4, and then we've got this coax connection at the feed point here. Now, what I've done here is in actual fact, what I'm going to do is I'm just going to remove this. I'm going to have to do a few iterations and returns because I was playing around with the sizing of it and the segmentation density to start off with. So this is just the pure clean fed dipole that would be theoretically fine with a balanced feed point. So we've got a 12.19 dB, nice clean pattern, and SWR is all hunky-dory and nice and clean. So we've got that nice wide flat dip that we saw a few weeks ago. So let me go and return this piece of coax back on again. I'm going to need to get it down to a point where we that's it. I think that's where we are. So now let's have a look with this coax connected, and just to look at the current distribution again, and you can see that in the driven element you've got this snapped, if you like, current distribution here, and then there's some of that radiation through the coax. Now you just saw that pop up, but if you look at the difference in the pattern now and how this rear end has exploded. So basically, not have you just dropped from 12.19 dB of gain to 10.65, your front to back has dropped from 30 odd dB to 13.96, and the whole back of the antenna has exploded to this 14 dB down on the main lobe. So now, just through leaving off a balun, you've now got a much noisier antenna with less gain. So let's just have a look at the SWR in this case, and it can vary, you know, side to side or each way it goes. Now this instance, you can see it's still fairly flat. It's just 1.5 to 1 now. Now depending on the routing of the coax and how long the coax is, that will vary. Because of course you're varying and altering the length of the driven element. So let's take a situation where, okay, we've got a balun in place, but we don't know if it works. And I'm kind of intruding now onto some of the other areas that I was going to cover into some of the other drill down subjects on baluns, but I'm going to touch on it anyway because I think it's important. Let's say, for instance, you've wound a choke, and which would be a few turns of coax at the feed point. Now the point here is that a choke, or ugly balun as they're called when it's an air wound piece of coax at the feed point, it's not just a case of throwing a few turns together and it works. They tend to be very narrow banded, and you need to get it right and ideally measure the choking impedance of that choke to make sure that it is successfully working where you want it to work. But there is a simple way to see if that's working or not. Now I'm assuming that in most cases, what I do if I was making a air wound choke, I would use like a household can. It may be a Mr. Sheen can for somebody in the UK, or for outside of that a WD-40 can, and use some sellotape to hold 3 or 4 long cable ties around the outside of that can, and then I would wrap my coax cable however many turns, 5 or 6 turns around one of those. If it's for 6 meters, would probably be there or thereabouts, and then connect up the cable ties and pull them not too tightly so that it dents the coax cable, but tightly enough to form an air choke, and then pull the can out, so you now have an air wound choke. So how you would test that to see if it's actually working, a lot of people that have very expensive equipment would cringe at this, but the simplest things sometimes work, and you don't need to have all of the test and measurement equipment that would otherwise be needed. But let's say, for instance, you've got that in place and you want to see if it's working. The easiest way to do that is run it on an analyzer, or with a transmitter where you've got the SWR meter that you can see all of the time, or you'd probably need some assistance with that. And if you was to put your hand around the coax on the shack side of that choke and the SWR changes, then you still have common mode currents on that cable, the other side of the choke, and it's not doing its job. So you would put another turn on and check it again, put another turn on, check it again, or it might be that you've got to take them off. But it's a long-winded way of doing it, but that's how you can work that out to make sure that everything is okay and working as it should. Now, there is a correct and a wrong procedure for installing said chokes like this, which will mean that they either work or they don't work, and I'm going to cover that probably in the next one, but I'm going to leave it there for the moment just to let you have a look again just at the before and afters of this said Yagi with the coax. So we'll run the plot again, real poor pattern, and we can see the current distribution that's interrupted in the pink lines where it's broken. And then if we remove that coax and we'll gut it again, where is it? Undo, and then undo from the top, and we get our nice pattern back again. So ideal world, that's what you're going to get and that would be how it would be with the most perfect of baluns. The choke is a nice simple one, but it's not always the most effective. Some of the baluns, as with the one that we discussed in the last video, work extremely well to get much closer representation to what we're seeing here. But I'm going to cover some fully symmetrical baluns as well as we go forward in the coming weeks, which you can build very easily yourself too. So the next one is going to be on the installation and placement of the choke balun to ensure that you don't impede its functionality and you get this pattern that we're looking at now on the screen rather than the one we had on here previously. Okay, so that's it for today. If you enjoyed the video, please do like and follow, and we'll see you on the next one. Cheers for now.